review, we've been looking at the basically Newton's second law here, that the sum of the forces acting on an object is equal to its mass times its acceleration. And the forces involved were the frictional force based on the velocity. Dx dt is the velocity, so bx prime, and the spring force on the object, which is just going to be k times the displacement, and this forms a differential equation. And when we solve these differential equations, we just happen to know that a form of the solution that works is x equals a e to the rt. And when you plug that in, you see that r dropping out of this thing, things cancel, and we're actually able to solve for r. And r is negative b plus or minus square root of b squared minus 4mk over 2m, which is similar in essence to the quadratic formula. Now, we already discussed the critically damped case where b squared minus 4mk is equal to 0, but b squared minus 4mk is less than 0 case. This here is going to give us a imaginary number when we take the square root of a negative number, and it's also the underdamped case where we get oscillations. If b squared minus 4mk is greater than 0, we get the overdamped case. Now, what I'm really interested in right now is the underdamped case, and because what we'd like to establish is two things. We want we're basically going to end up with an equation of the form e to the alpha plus or minus omega t, I omega t. And in essence, what this turns out to be, instead of a e to the alpha plus or minus I omega t, we will end up with a e to the alpha t cosine omega t plus some other function b e to the alpha t sine omega t. Notice that this capital A, there's only one constant here, and it's divided into the plus and minus, but there's actually two terms that are here, a plus I omega t and a minus I omega t. And it turns out that this expression is a complex expression, but the only part of it that we can see in the real world is the real part, and the real part can be expressed in terms of two functions, a cosine and a sine. And since we will almost always assign like a starting point, we'll either assign, well, there's basically two situations. We can hold the spring out, and let the object go at time 0, in which case will be interested in cosine omega t, or we can have the object at equilibrium and give it a hard shove, in which case we'll be using the sine omega t. So probably we'll use one or the other, not both. Anything in between that, for instance, if we assigned both a initial velocity and an initial position, we would use both the cosine omega t and the sine omega t. So the only thing remaining is to figure out what is alpha and omega. So all we're going to do there is just take this r, or this quadratic formula, and convert it into a real and imaginary part. So if b squared minus 4mk is less than 0, then the real part of this is going to be alpha equals negative b over 2m, and omega is going to be square root of b squared minus 4mk over 2m. So let's show an example. I'll set b equals 1 for the coefficient of velocity friction, which would be in newtons per meter per second. K equals 1 will be the spring constant in newtons per meter. And then m equals 1, which will be 1 kilogram, the mass of the bob on the spring. Now we'll be taking our alpha being negative b over 2m, and our omega equals b squared minus 4mk over 2m. And what do we get? We get, well, I need to remove the semicolon so I can see the answer. And we see here that alpha is negative 1/2 and omega is I square root of 3 over 2. Now actually I should have probably reversed that, so because we already know that b squared minus 4mk is less than 0, so we don't want to have that imaginary. So I will change that from b squared minus 4mk to 4mk minus b squared. Now let's see if we can get an idea of what the plot looks like by plotting, say, e to the alpha t cosine omega t from t equals 0 to 20, and we can see that this comes out to come way down and then oscillate back up and down for a little bit. I'll change the plot range because this is going very, very sensitive. The plot range in negative 1 to 1 shows it coming down and quickly dissipating as you get towards the edge there. Now, how could we make this thing really sproing back and forth a lot more? By increasing the spring constant. Let's give the spring constant about 10 times as much value. We'll change that to 10, and it should bounce a lot faster. And you see it bouncing quite a bit faster. And then if we want to kind of slow it down, I guess we could change the mass. So I'll make the mass about 5, say, and now it oscillates quite a bit slower. And then if we want to damp this thing so that it doesn't really oscillate, we could increase this friction a whole lot. Let's change that to 100. I think this thing might break down if I do this because we'd need to, because that'll make omega be real. So yeah, that'll break it because we made that under the assumption that 4mk was under. It does still give some kind of slowly sloping down thing, but I don't think it's correct because it's got an omega that is a non-real value here. So I'm going to put that back the way it was, and then let's look at the case where b is 100 and see what happens. I'll bring that down here and start a new example. Changing b to 100. Now what we're going to get out of this is we're going to have two roots, negative b plus b squared minus 4mk over 2m and negative b minus b squared minus 4mk over 2m. And this time I'm going to draw two plots, one for e to the r1t and e to the r2t on the same graph. And you'll see one of them gives us let's numerically evaluate those two things. You can see one of them takes a really long time to cut down, and the other one takes a really short time to cut down. Adding a little bit more feedback, you can see that R1 is negative 0.1, which creates a very slow decay, whereas R2 is negative 19.9, which would create an extremely fast decay. Now at this time, unfortunately, I am unable to come up with a precise explanation for what these two different decay rates would be. My understanding is that you would have a linear combination of both prospects, so if I added those together, well, basically we could assume that the whole x of t would be some kind of linear combination of a e to the r1 of t, or r1 times t, plus b e to the r2 times t. But I'm not sure how you would decide which one of these two decay rates is going to dominate. Based on the fact that I've been reading that the critically damped happens somewhere, would happen when these two values are the same, when b squared minus 4mk is 0. I would guess that in the non-critically damped case, the slower decay rate dominates, which means that in general the object will not come to equilibrium very quickly, but I still feel like there should be some kind of physical explanation for this decay rate, and in particular why that decay rate is why would this decay rate be eliminated. So I may think about that for the next couple of days.